Welcome back. Okay, so this is the third class we're going to do on transition elements. So this is Friday's class. I hope you've been able to keep up so far. Nobody sent me any questions on what I have presented so far, so I guess there's no problem. If you do have a problem, of course, always tell me what the problem is and we can discuss it and so on. Okay, but you guys are super smart, so I guess you don't have any problem so far. Okay, so here's Friday's class. Previously, I talked about the color of these complexes. I just kind of give you verbal descriptions, and I gave you a bit of a pictorial description of what happens here. I wasn't very satisfied with all this just text only. It's better to see it in the flesh, so I made that other document for you, which is, where's it gone? Which is here, okay. So I'm showing you the stated compounds in the syllabus and the actual colors that you can expect. Even this isn't perfect because, like I said, it does depend on the concentration as to exactly how it appears. Okay, you can make this like super intense. It almost begins to look a bit red. You can make it look super pale. And it looks like a, well, extremely pale pink color like Mn2 plus aqueous solutions. So this is a kind of a middle of the road kind of thing. It's reasonably concentrated. It's not too dilute. So you get a good appreciation of a typical color that you might expect. So this was a cobalt salt, cobalt 2 plus. It was actually an aqua salt. So the anion had dissociated from the cation. The anion and the cation are floating around independently in this mixture. And therefore the CO2 plus ion gets attacked by water molecules. We get an aqua complex. So this pink color is characteristic of cobalt 2 plus aqua complexes. All right, so then some NaOH was added into this, and you can see that it makes a blue precipitate. Kind of look a bit darker than this. It kind of even the angle that you look at this at on a screen can make it look a bit different. I'm moving my head around at the moment, and from one angle it looks like a dark blue. Another angle it looks like a light blue. So even these diagrams are not perfect, but you can definitely see there's like some bluish stuff in there. And if you throw in some hydroxide, that is what you will see in the beginning. And you can also see in this picture that it's beginning to actually look a little bit gray as well at the same time. I did say it kind of goes into a grayish color. But that gray is just the subsidence of the blue in favor of the final pink precipitate. So it's just kind of like changing from blue into pink. So it looks like it's a bit gray in between. Okay, but clearly there's a precipitate there, right? So if you give it a good shake, then we move down here, then the kind of blue precipitate disperses evenly throughout the solution. And if you just leave it, then it kind of, well, the gray color might kick in at the bottom where the precipitate tends to accumulate. But again, this was shaken and it's just left to stand, and it turns into a pinkish color. So the reason why you see a couple of colors here is because the water ligands in the aqua complex, the water molecules which have attacked the central metal cation, they actually begin to kind of slowly leave. So we're actually getting different versions of complexes on the way to the final product. So that's why sometimes you get these intermediate looking things going on. All right. So it's important to recognize the initial observation, the blue precipitate that's formed, and then it's important to understand the final color that you will get at the end. Not all of them do this kind of changing thing. Some of them just stay the way they are, but a few of them do change along the way. So you need to be aware of those intermediate steps. All right, so we kind of get a pinkish, peachy pinkish kind of color at the end, and that's actually the cobalt hydroxide. It's all the water molecules have left the cation now. They're no longer bonded to it, and we just get the insoluble hydroxide just beginning to settle at the bottom. And this is kind of what it would look like if it's pure. It's a nice pinkish color, cobalt hydroxide. It's a solid. Okay, so it's been filtered off and dried. It's still got some water in there, however. It's very hard to get these completely dry. Okay. So that was cobalt with hydroxide. So here's cobalt with ammonia. Now this is also a bit tricky because we have interacting colors present here at the same time. We've got this precipitate forming when we add ammonia, and obviously we have to see that through this pink colored solution. So the actual color of this can be a bit misleading. It's kind of, it looks green, right? Like all the combinations and stuff there, but it's got a bluish tint to it. Okay, so we would say green. All right, so it's not like the hydroxide precipitate, which was blue, even though the same kind of process is going on here. Hydroxide ions are attacking the aqua complex. But because we've got this ammonia stuff in here and this particular color is shining through this pink light, it takes on a greenish appearance. It is a bit tricky to comprehend that, but that's just the way it is. Okay, so we have this green precipitate inside it. We can still see some of the cobalt aqua solution down here. It hasn't fully mixed properly yet. And if you add more and more ammonia, that precipitate will disappear. So then we just end up with a charged complex. Remember, these charged complexes are soluble because they make ion dipole interactions with water. So when the initial hydroxides get displaced by the excess ammonia, just like we saw before, then you get this transparent brownish colored solution. Again, it depends on the concentration. Sometimes it looks orangey brown, sometimes it looks kind of like a wooden brown, sometimes like a bit of a sandy brown if it's very low in concentration. So there's two pictures here from independent sources as to what this aqua complex, the ammonia complex looks like. And if you go to this link, there's a video where these cobalt compounds are actually shown on the spot reaction. So it's a good reference point. And frankly, chemistry is actually a very good website for practical discussion. Okay. Theory also, of course. A lot of instrumentation videos here. I highly recommend that you go to this site and check it out. Okay, so over time, this brown stuff actually oxidizes further. It goes from the cobalt hexaamine 2+ complex, which is this one here. Let me zoom in a bit. So we go from this, which has got a 2+ charge, it's ionic, soluble, and it makes the 3+ charge. So the only difference really is this charge. The ligands stay the same, but the cobalt has actually undergone an oxidation with the oxygen in the air, and the oxygen dissolved in the water. Remember that paper 5 we did the other day? The oxygen was dissolving in the river water. So we also have some oxygen present here. And that helps oxidize the cobalt inside that solution. So it goes dark brown over time, much darker than this. So this is the 2+ version. The 3+ version will look a bit more like this, but even more intense. It gets so brown, it almost begins to look browny black. It gets hard to see through. Okay, so that was the kind of the cobalt things. The aqua with hydroxide, the aqua with ammonia, and now we're going to look at the aqua with chloride ions. Okay, so we take some, well, you can take any cobalt compound and you add some water to it. I'm not going to go through this whole thing. You can read it. It's described pretty well here. And again, we end up with an aqua complex. Okay, the aqua ion is usually the one that's most favorable to bond to the metal in terms of ordinary chemicals that we have in the lab. The ammonia is a little bit better, which will tend to displace the water eventually. We'll look at the relative strength of these things at being able to displace water ligands. Okay, so here we have an aqua complex, and we're going to add loads and loads of chloride ions, and we'll end up with this blue stuff, this cobalt chloride blue aqua complex. So you are kind of expected to know the shape of this thing and its color. And I did mention on the notes it was thermally unstable. So if you change the temperature of this, even by a small range, you can actually get these things interconverting into their respective colors. We'll probably do this in the lab at some stage. All right, so know the colors, and of course, obviously know the chemical equations for these processes that I've described so far. I'll give you a more complete list later. I've just kind of basically summarized them so far. But here's a complete reaction equation. So that's the kind of the cobalt ones. Ammonia, hydroxide, and chloride. We do the same thing for copper. These are two elements specifically stated, copper and cobalt. So we can get our aqua complex of copper, which is this blue colored solution. We add hydroxide or ammonia, and the hydroxide inside of the ammonia or the hydroxide directly inside of sodium hydroxide solution will make a precipitate, this pale blue precipitate. And if we, in the case of ammonia, we keep on adding ammonia, eventually the concentration of ammonia gets so big it will displace any hydroxide that was formed, and we get this deep blue solution, royal blue solution. And here's all the precipitates gone away now. You can see it's a beautiful color. It looks even better in person when you see it right in front of you. It's quite an attractive color. Here's an alternative version of that. Here's the aqua complex. Here's some of the copper hydroxide precipitate, and here's the amine complex, the tetraamine. And remember the shape of that thing? It's kind of distorted, the distorted octahedral. We still have water ligands present in this complex. I don't care if you see a source somewhere that says you only have ammonia there. That's not true. There's still 2 water ligands there. And that's what you're expected to do for Cambridge. Alright, so again we can do the chloride thing. I mentioned it kind of, if it's highly concentrated or pure CuCl4 2-, then it looks yellow. But on the way there, it kind of has this green color. So we have the mix of the yellow that we produced in small quantities and the original copper 2+ aqua complex. They mix together to give this greenish appearance. And here's another example of the compound changing from aqua into the tetrachloro. You can see it's got some regions of yellowness, but there's still some regions of blueness or slightly greenness here. So it's not mixed, it's not a homogeneous solution. We do have different concentrations present in that tube, hence we get different variations in color. If we mixed it, of course, it would be homogeneous, it would just look like one color. And if we keep on adding loads and loads and loads and loads of chloride ions, eventually we might get to a kind of a nice yellowish color. So this is super concentrated. My guess is that they took a solid copper 2+ salt and they directly added HCl, conc, to it to get this beautiful strong color. Because in the lab it's actually very hard to get a nice, pretty much pure yellow. It's very common we kind of almost get to a nice yellow color. And if you're careful, you can actually make it look almost yellow. Alright, so the color of these compounds is actually due to the ligand, the thing that's bonded to the metal ion. Remember, ligand is just basically a nucleophile, right? It's a species of a pair of electrons which can make a dative bond, or a coordinate bond, as it's called in this topic, to the central metal cation. If you remove that ligand, well, then it will actually become decolorized. So if you take copper sulfate, which normally exists as a hydrated salt, we have CuSO4.5H2O, and we heat it up, the water will kind of come off, and we'll be left with anhydrous copper sulfate, which is white. So the only difference between the white one and the blue one is that we have this ligand present which is bonding to the copper, and that causes it to have color. We'll see this in more detail later. Alright, so that's what I sent you yesterday. I hope you managed to go through it, and if you didn't, then you have done it now. Okay, so let's get back on with some notes. So in my syllabus, where's the syllabus gone? Come back, syllabus. Okay. Okay. Let me just copy this across. So we've done point 1 in 28.2. So now we're going to look at this, which we've kind of already done. Define the term ligand as a species. So it's telling you how to define it. Good. So this is just a memorization thing. A species which contains a lone pair of electrons which can form a dative covalent bond to a central metal atom or ion. I still don't like that word atom. I still feel a bit uncertain about that word, but if that's what Cambridge will accept, fair enough. So don't forget, the alternative wording for a dative bond is a coordinate bond. What am I So I'm surprised to see them revert back to dative bond so quickly. Usually they stick with coordinate bond. So they themselves seem to have forgotten that they were trying to encourage the use of this term. They've gone back to the old term. So we already know this. That's great. It's always nice when they already tell you what you've already learned from somewhere else in the syllabus. So the next part in the syllabus is something to do with denticity. So we need to understand the terms monodentate. Mono, I'm sure you all understand what that means by now. One. Dentate essentially means a bite, one tooth. A bite. Not a computer bite, but an actual bite. Gigit bite. So some ligands have got one bite or one tooth. What does that mean? They have one pair of electrons which can make a dative bond. So examples of a monodentate ligand are given here. Water. Even though water has got two lone pairs of electrons on it, it's still just a monodentate ligand because it will only use one of them to bond to a metal cation. You will not get something like this. You will not have a metal with two bonds to a water molecule, because that will be the result. Let me just shuffle this across a bit. I'll give you the result of the first interaction. So let's move this to the side. So if we did this water molecule bonding to the M, we will get this. And we've seen this kind of thing before in a number of different topics. So let me use the kind of arrow to show a dative bond. There we go. So oxygen's got 3 bonds, so we know actually there will be a positive charge on there. And now the charge on the M will be N-1. So if you want to be fussy and allocate the charges to it, then we can get that kind of thing. And we've seen this thing before with hydrolysis of esters. I think we did that last year. We had like a C double bond O, O, R. Okay, and we had a water ligand, or we could use a hydroxide ligand. Hydroxide is going to do this much better than water because it's a better nucleophile, so let's use that instead. So we have seen this kind of thing before. All right. I did mention it. It's not formally within the AS syllabus. I did mention it in class when I was going through mechanisms with you. So a pi bond actually will break. The electrons would go onto the most electronegative element. Hydroxide will attach on, and the other group hasn't done anything at the moment. Okay, so that was the first thing that happened. Nucleophilic attack on the delta plus carbon. The weak pi bond breaks. That was the second thing that happened, and we end up with this intermediate. And this tends not to stay like that. It's got 3 electronegative atoms on the same carbon, so it's not a very stable arrangement. Things can kind of like shuffle around, and there are many ways you can show this, but this is just one way. It's probably a very bad way of doing it, but so we'll actually end up with a pi bond restored. This group gets kicked off because that pair of electrons attacks the H, and we end up with an O minus. So this will be alkaline hydrolysis of esters. We'll actually end up with a carboxylate anion. There's going to be something down here. I haven't shown it, but there will be something there. Okay, so yeah, we can do that. We can get O's making a single dative bond to some kind of species. Okay, so It can happen with water. It can happen with hydroxide. It can happen with a number of oxygen-based species. So that's fine. Making one is fine. But two, not in ordinary conditions. No way. So this one, you don't get both pairs of electrons going from the oxygen, because the result would be an O2 plus species. It's bad enough having a positive on an oxygen, but having 2 plus on an oxygen on the second most electronegative element and giving those electrons to something else which is not as electronegative as oxygen, then there's a cat's chance in hell of that happening. It's just not gonna happen under normal circumstances. So that's why water, even though it has 2 pairs of electrons, only one of them will be active. The oxygen cannot really sustain that 2 plus charge. So it's a monodentate. Only one of these gets used. So it only makes one bond. One bond. Only from H2O. So it bites the metal once, so it's a monodentate ligand. Other monodentate ligands, well, ammonia is obviously, it has 1 pair of electrons on it, so there's no question about whether 2 of the lone pairs can do it, because there isn't 2 lone pairs, there's only 1. So obviously that can attack a metal, put some kind of charge on it, and we can make a dative bond. We can put the charges on it if we wish, and if you really want to do that, you will do this. So the N has lost electron density by sharing it with the M. The M has gained electron density by taking in the lone pair from the N. So as always, when you gain electron density in this manner, you become more negative by 1. So the charge is now N minus 1 plus. It's become more negative, and that has become more positive by 1. So ammonia is monodentate also, of course. You could probably instantly tell that just by looking at the molecule. He didn't need me to tell you that. Other monodentates, of course, are hydroxide and amines. Those very religious molecules. Amines. Here we go. They also have a single lone pair on the N, so they're also monodentate. They all bite to metal once. Chloride ions and bromide ions, they're also monodentates. Now these are pretty lousy ligands because they were lousy nucleophiles. You don't normally get Cl- coming in and attacking stuff because it's perfectly happy the way it is. It's got its full outer shell already. It's quite electronegative. It doesn't really want to give up that electron density again if it can help it. Bromide ions, they're quite bulky, right? They're not particularly great nucleophiles either, but they still have lone pairs on them, as the chlorine does. But once again, it will only use one of them. Now we will come across compounds later on. Did we do this last year? Oh, crikey, I can't remember. I think we might have looked at this. This is the chlorate 7 anion. So chlorine can actually make double bonds with oxygen. This is Cl. Okay, so we can get like +7 oxidation states for chlorine, but it's not a stable compound. It's like super bleach. If you thought bleach was bad, which only has the +1 oxidation state, this bleach is awful. There's a movie where they had this. What was it called? 10 Cloverfield or something like that. Let me just have a quick look on my computer. 10 Cloverfield Lane. I thought it was an excellent movie. So if you're interested and you want to see this compound and what it can possibly do, 10 Cloverfield Lane. Just watch it. Don't watch any previews. Don't have the ending spoiled, right? It's got an amazing ending. Okay. Anyway, so it's a monodentate ligand, chloride ions, monodentate. Even though chlorine can use its other electrons to make other bonds in this case. Okay, so let's just scrub that. Bye-bye, movie. Okay, bromide ions, iodine ions are all the same. All these halogens can make a single bond to a metal ion. But they're not very good at doing it. They're reasonably happy the way they are. Another monodentate ligand, common to A level, is the cyanide ion. And we've seen this ion a few times. And this is actually a very good nucleophile, isn't it? It's a very good nucleophile. Therefore, it's going to be a very good ligand. It's almost a direct correlation between the nucleophilicity of something and the ligand strength. They're almost exactly the same. So this can also make a single bond to some kind of metal ion. And this is actually what makes cyanide very dangerous, because in your body you have many metals. One of them in particular is iron. And it usually exists in the form of iron 2 plus or iron 3 plus. It's found in the blood, right? So, cyanide, if it sees iron, it likes iron a lot. It's going to just bang, it's going to stick onto the iron and it will stay there. There's almost nothing in the body which can actually remove that again. So if you're exposed to cyanide, it starts to eat away at the iron in your body, so you can't really breathe properly. There's not enough oxygen transportation in the body. So that's why cyanide is particularly dangerous. And whether you breathe cyanide containing compounds in or you ingest it in food and stuff like that, the same result occurs. It attacks and hunts out the iron, plus other metals as well, in the body. So the body chemistry is heavily disrupted. So stay away from cyanide ions. It's not very good for health. Okay, so it's also monodentate. Now we get onto the bidentates. Oops. Bidentate ligand. There's a list of them here. Just copy and paste it. Okay. We have some quite interesting molecules. I don't think we've seen this before. This thing. 1,2-diaminoethane. So what does that look like? This molecule will appear in quite a few places in A2. So we have an amine at the end of this hydrocarbon, but we also had an amine at the beginning of it. It's a diamine. There's two functional groups on it. Remember when we looked at reactions of alkenes? We could actually make a diol using dilute, cold potassium permanganate, and we'd get two functional groups on the carbons in the alkene. This is the same, but instead of having an OH group on the CC unit, we have amine groups instead. So if you're clever, you would know how to make this from an alkene. First of all, you would make that, and then we need to have some. We can't remove OH directly for NH2, so we would turn that into using PCl5. Now you've made that, then you can use excess hot concentrated ethanolic ammonia, and we'll get double replacement of those chlorines to give this diamine. This is a synthesis. We will have to master all these chemical pathways later. So, and we'll do that when we do organic. Okay, so we have this diamine. Now, this is a very common molecule, as I said. It's so common we like to give it its own symbol. We call it En. I used to have a student called N. So when we were discussing this topic, she would often kind of like wake up. She thought her name was being called all the time. So, yeah. Okay, so this is bidentate. It can make two bonds to a metal. molecule is flexible enough for it to kind of bend around and allow it to make a bond on either side of the metal ion. So here's our kind of ligand encased in this kind of bubble, and it's making two dative bonds, a bit messy, to the metal ion using its lone pair on each of the ends. So it's bidentate. And when we looked at the aqua complex, we realized you can have 6 ligands stuck on these metals. Well, we can actually take 3 of these bidentate ligands, and we can occupy all the spaces on that metal. So if we have some kind of metal ion, we can have the ligand down here, and we just use this kind of squiggly line to represent the rest of the molecule. We don't really care what is in between these ends, and we can do that on this position over here. Didn't draw this particularly carefully. Let me draw it again more carefully just to make it easier for me to draw later on. Okay. So remember, we have axial positions and equatorial positions. So I'm occupying one axial and one equatorial. This one here can occupy an equatorial, maybe the other axial. So some connection between these ends. I don't care what it is. And finally, we have the other 2 equatorial positions. It can also be occupied by a bidentate ligand. So here we see 3 bidentate ligands attacking a metal, and we end up with an octahedral shaped complex. Look at the bonding. We have axials and equatorials. And there are various ways in which this can happen, various orientations, which actually leads us to isomers. We can get isomers for these compounds, not just organic molecules. No, transition element complexes can show isomeric behaviors. And they often have many more ways of showing isomers compared to the organics. So it's very fertile ground for isomers. Okay, so bidentate ligands can do this. There are tridentate ligands too. They're not really mentioned in the syllabus, but you could probably imagine what one would be. If you had this, that would be bidentate. So why don't we just like add an extra thing here? So we end up with 3 ends in this molecule. They have 3 lone pairs. This will be a tridentate molecule. I can't be bothered to show all the H's, but there are H's in the places where there is no bonds shown. So that amine, that's also an amine. It's a primary amine and also a secondary amine. So it's a mixed amine. That can be a tridentate ligand. We typically don't normally talk about tridentates. We normally talk about monos, bis, and hexas. So mono is pretty much done. Bidentate. Oops, I forgot. There's one more common one. How did I forget this? This is very important. So remember this molecule. Again, you should remember how to make that from C double bond C. We can go to the diol. Then we can oxidize that further using something like potassium dichromate. In acidic conditions, we can make this dicarboxylic acid. So this is called ethane dioic acid. It's a diprotic acid. It has 2 acidic protons. And you should be able to spot what those acidic protons are. It's obviously the one at the end of the COOH group. Sometimes this is abbreviated to something that looks a bit weird the first time you see it. Sometimes it looks like this, COOH twice. And I have seen this in a few exams, so be prepared to see this weird way of representing this molecule. Alright? So be careful. This is the same as that. Now, because it's an acid, acids react with bases to make salts. You can actually make a salt of this compound. You can take some sodium hydroxide, 2 moles equivalent for every 1 mole of the diprotic acid, and you can make the anion. If you want, you can put the sodium there. No problem with that. But if you dissolve this in water, of course the sodium is a spectator ion. It'll just float happily away. It won't stay associated with this O-. We'll get ion dipole bonding forming, so it will disrupt this ionic attraction. And we're left with this, the ox ligand. So we've got lone pairs. We've got 3 lone pairs on the O. We don't normally have to show all of them, just one of them is usually enough. Same thing is present here. You can count the electrons yourself like we did for AS, and you can determine that there'll be 3 lone pairs. One of the electrons in here obviously will be gained from the sodium if you react them directly together. So we have this. The point is that now this acts a bit like the En, and it can make 2 bonds to a metal cation. So this is also bidentate ligand. And just like the ethyl diamine, which I didn't name, so let's just quickly write that again. NC. Okay, didn't really want to write the whole thing, but I don't think I've got any choice. Okay, so this is ethyl to amine. Or En, as we mentioned before, N. It's normally said En rather than just N, actually. But we have that bidentate ligand, and you can see that this En is actually just a nitrogen version of this ox. So this is called ox. It's the oxalate anion. It's the old name for ethane dioate anion. Oxalate. It's kind of the old name. Oxalic acid is the thing it came from. That's the old name for ethane dioic acid. When chemistry used weird symbols and had completely weird names. It still kind of does today, but not as bad as before. So this is just the oxygen version of that. But it is charged, okay? So we have COO minus twice, or another way that's written, COO twice 2 minus, which is a horrible way of representing it. It looks even more confusing than before, but you'll often see these different ways of describing it. So ox is also a very powerful ligand. I'm not sure if you have been to Europe, and if you have been to Europe, maybe there's a vegetable that you ate. I think it's a vegetable rather than a fruit. So there's something called rhubarb. I'm not sure if you've eaten it before. It's quite commonly eaten with custard. Rhubarb and custard is quite a nice thing. This stuff kind of grows in the wild. A lot of people eat it, but they do not eat the stalks. The green thing, the leaves. That's what they're called. Oh my god! They eat the stalk, the nice pink-colored stalk. If they eat the green stuff, they're in trouble, because the green stuff contains an oxalic acid. It contains ox. So if it contains ox and you eat it, well, it's going to be a bit like cyanide. It will start sticking to the metal ions in your body, and it will disrupt your body chemistry, and you can actually get quite sick. You can actually even die if you eat too much of it. So if you want to eat rhubarb, no problem, just don't eat the leaves. That's all. Okay, so that's a bidentate ligand. Now, the king of all ligands is EDTA. EDTA. And EDTA, a bit like ox, actually comes with a charge. It acts as a ligand when it has a 4- charge. So this is what I call the king of ligands. Don't use that in exams. The examiner will say, what are they talking about? Just between us, okay? So I think you need to draw the structure of this, and it's quite big, but it's very symmetrical, so it's actually not too difficult to draw. So at the center of it is an EN molecule. So if you remember EN, which is quite simple, right? That's absolutely compulsory that you remember that one. There's our base structure. CH2, CH2, and NH2 on either end of those carbons. Okay, so what we're going to do is we're going to chop off a H, and we're going to replace it with an acetate group. Where are we? My drawing isn't very good, so I'm just wondering if it would be quicker just to paste one over. So yeah, I'll look for EDTA. It's going to save me a lot of work. If I can find a good diagram, that is. Oh my god, these diagrams are not very nice. This is probably the most nice looking one. Well, that's not too bad, I suppose. Nah, never mind. Okay, well, let's stick with the one that I have already chosen. Okay, so it has an acetate group where we chop off the H's on the end. So it looks a bit like this. So you can see the EN hiding inside there. There's the EN bit with the H's chopped off. This is an acetate group. And as you can see, there are 4 of them. So when it comes to naming organic things, if you've got 4 of something, it's usually tetra. That's what the T stands for. It's tetra. I'm so glad I managed to copy and paste this diagram. This would be a nightmare to draw nice and neatly. And the A, what does that stand for? Tetra. Well, it's tetraacetate, isn't it? No Nobel Prize for that, I'm afraid. Acetate group. What is acetate? The E is ethyl. I'm running out of colors. Ethyl. The D is the diamine part. I've seen amine spelled with 2 M's and 1 M. I don't think it really matters. Nobody cares. I like to spell it with 2. Not sure why, but anyway. So ethyl diamine tetraacetate. It's even longer word than electronegativity. So good for Scrabble players. That is what this molecule is. Now, this is not actually EDTA 4- because it has the acidic protons on it. So actually what we need to do really to make it into the ligand form with 6 bonds available to make to a metal ion, we need to get rid of that acidic hydrogen at the end. These COOH groups, of course, are acidic, right? All COOH groups are acidic. So we're going to remove the acidic proton, and that will leave behind an anion. And then put O-. So this is important, because this O- is one of the places where it makes a bond to a metal. So each acetate group contains an O- now. Okay, that's why it's got a 4- charge on the ligand form of EDTA, not the parent acid, which has got no charge. So this is the ligand form. It's charged. Okay, and there's also the original electrons on the En. They can also be used to make a dative bond. So it is hexadentate. You can make 6 bonds to a metal. one here, one here. That one can also attack a metal. This one can attack a metal. We have 6 dative bonds which could be made to a metal. And the molecule is long enough for it to be able to surround a metal ion pretty much completely. It's long enough and flexible enough. It can bend. Remember, the rotation around a single covalent bond is pretty much unrestricted. That can spin around, and so can this. They can all spin around when they have single bonds. So the molecule can kind of wrap itself around. It can morph itself around a metal ion. And I'll go back to what do you call it? Image search. It's not Google. It's DuckDuckGo. I'm not sure if you use that, but I like it. It tends to have good filtering content on it. Oops. What am I doing? Yeah, I'm trying to show this image. Where's it disappeared? There it is. So you can see that this molecule is an EDTA molecule. It's wrapped itself around. The ends of the EN part have made a bond to the metal ion. Oops, why does that keep on happening? So here's the kind of the N functionality. Oh, that's not an image, that's right. Okay, that's so big. Okay, so the EN part of this molecule is here. And the acetate groups are sticking out, and they can adopt the equatorial positions and attack and the axial positions as well. So this EDTA is actually very important. Because it can be used to treat heavy metal poisoning. Now, in various parts of the world, heavy metal contamination is a problem in the water supply. And some people, when they drink polluted water, they ingest heavy metals like lead, tin. Even aluminium is not a very good metal. You don't want to drink metals. S block ones are not too bad because they're normally soluble. They can be expelled from the body easily. But other metals usually form precipitates, or they interfere with the enzyme processes in the body and so on. So if you drink EDTA, it's very good at displacing other ligands. So if you've ingested lead and the lead has somehow managed to interact with your enzymes, so it's deactivating your enzymes, stopping you from living and functioning normally, the EDTA can actually displace those ligands and surround the lead. So this is just showing you EDTA can surround the lead. Okay, so it frees up the enzyme, and because it's got a 4- charge on it, then when it surrounds most metals, they will still have a residual charge. So we might have had like a lead 2+. In that case, once this complex is formed, it'll be 2-. The lead 2+ takes away 2 of the negatives from the EDTA 4-, leaving 2-, which of course will be soluble. So it's easily excreted by the body. So heavy metals can be treated, heavy metal poisoning can be treated using EDTA. It's an excellent way of displacing other ligands. And one of the reasons behind this is our old friend entropy. It's mostly, well, not mostly, but the presence of entropy in this reaction is very significant. So entropy to the rescue. So that's a hexadentate ligand, EDTA. Hexadentate, it makes 6 bites to a single metal. 6 bonds, if you like, to a metal ion. And this is what we mean by coordination number. It's connected to this kind of stuff. Coordination number is the number of bonds a metal ion has to ligands. So, if we have the silver diamine complex, which you've come across already, okay, this is it's monodentate ligand. Each ligand makes one bond to the silver, but the coordination number is 2. Why is it 2? Because remember, it has one bond to each NH3, and there are 2 of those bonds in total. So a monodentate ligand is present, but 2 bonds in total are formed. So what about this EN thing? If we, let me just copy and paste again, because I'm not going to be able to draw it anywhere near as semi-badly as I did before. Okay, so here's our En surrounding this metal. Let me just copy and paste it. There we go. So the complex here is well, it's got 6 bonds in total. Therefore, coordination number is 6. And the ligand that we have is bidentate. So the coordination number 6, bidentate. And we can actually make statements about the shape of molecules based on the coordination number. So coordination number, we just abbreviate it to this. Coordination number and shape. Shape has a very important part to play in the chemistry of most molecules. So whenever we have coordination number of 6, this is the easy one. Even though it's a lot of bonds, the shape is always going to be octahedral. It doesn't matter if that octahedral shape comes from an En or 3 lots of bidentate ligands, or even 6 lots of monodentate ligands. It has 6 bonds in total. Alright, so that shape that results from this will always be octahedral. If the coordination number is 4, so it has 4 bonds to whatever ligands are present, then we have 2 possible shapes now. We have the familiar tetrahedral, but we also have square planar. So 4 is kind of a tricky one, and because it could be one or the other shape, Cambridge like to focus on this one in the hope that students will pick the wrong shape. Alright, bidentates, well, I've got a lot of combinations of this, but typically if you've got 3 of them, well, sorry, not just 2. No, I'll keep it simple. So this would be like an example of the silver one. That would be linear. So I'm just going to consider the monodentate ones at the beginning. And I think that's probably what Cambridge will stick to, because it can get a bit messy with singly bonded bidentate ligands with another single monodentate ligand. You can get weird combinations, but let's not go there. Okay, so of these shapes, you should be able to draw them. They are 3-dimensional, apart from the last one, of course. So you must always be able to draw an octahedral properly. So we have axials, which are drawn in this manner in the plane of drawing. We have equatorials, which can come out of the plane towards you. Let's just say L for ligand. Well, let's just consider monodentates. And then we also have bonds to ligands going into the plane away from you. So they're at the back. So that's your octahedral shape, which we have mentioned a few times already. Not only in A2, but in AS as well. Remember SF6? Sulfur hexafluoride. Okay, so we must be able to draw the shape. Sometimes you will see diagrams with a kind of a box in the center location. And sometimes you will see lines like this. Now these are just kind of like construction lines. They're just there to show you the shape. They are not bonds. So sometimes I don't like to see these things because it looks like there's bonds everywhere, right? But they're just construction or shape construction, if you want to be a bit more accurate. They emphasize the shape of the whole structure. So it's got this octahedral, kind of like double square base pyramid shape, one at the top, one at the bottom. All right, the next one, the tetrahedral. That's a piece of cake. We've been drawing tetrahedrals for quite a long time already. So we have a central metal ion. We have a classic tetrahedron. Please make sure that one bond goes into the paper, one bond comes out of the paper, and one bond, two bonds are in the plane of the paper. But try and draw the bonds in the plane of the paper in this orientation. Okay. So this is good. I think a few of you last year in the tracking test, if I remember correctly, you kind of did something that looked a bit like this. This is not good. So try to avoid it doing stuff like this. And of course, try to avoid doing stuff like this as well. I didn't show the ligands at the top. So try not to do this. Stuff like that. You're going to get yourself into trouble with bond angles, right? You're saying that you have these two like 180 degrees apart. That doesn't exist in a tetrahedral shape. Same kind of error is occurring here, right? 180? No, no way. So stick with a single convention when it comes to drawing tetrahedral shapes, and you're less likely to make mistakes. Alright, so don't do your own thing. Right. Even if it's correct, I still wouldn't advise you to do it. Stick with one way of doing it. Okay, what about the square planar? Well, as the name indicates, it's a planar molecule, and it's actually in the field of a square. So I'm just going to draw this outside box just as a guideline. So we have a ligand on each corner of the square. And in the center of the square we have our metal. So this is a three-dimensional shape. So these bonds closest to you, or at the bottom, are actually coming out of the plane. These ones are going into the plane at the back. So that's how you draw a square planar shape. You can draw it from above, a bird's eye view if you like. If you draw it from above, then of course everything will be in the same plane as you're looking down, and you could get away with drawing it like this. Bird's eye view. Is it hyphen? I'm not sure. Okay, but I wouldn't recommend that you really do this. Try and draw the bonds going into the plane and bonds coming out of the plane. So there's your square planar. Examples of this are nickel tetracyanide, I think, e.g. Nickel with 4 cyanides, 2 minus. You're not actually expected to be able to remember which complex has which shape. You'll be given clues as to what the shape is. So we'll get on to that soon, okay? And the linear one, well, that's a piece of cake, right? You can also have cyanides here, silver dicyanide, instead of just the ammonia one. It's also a linear complex. Oops. That will be minus, because the cyanide ligand is negatively charged. Okay, so that's denticity and coordination number and shapes. Now, students often ask me, square, planar, or tetrahedral? How do you know the answer? Well, this one shows, or it can show, optical activity, i.e. you can get optical isomers, here we get geometrical isomers. So you'll be given clues in the question. If they decide to probe this part of your knowledge, you'll be given clues as to whether or not this compound can make geometric isomers or whether some other compound can make opticals, and then that will give you clues to what shape it is. They may also talk about the orbitals, the energy of the orbitals. And from that information you can also deduce whether it's square, planar, or tetrahedral. When we look at the colors of these compounds, we'll mention that way of doing it. Right, so I think I'll leave it there for today. We've done quite a lot of stuff. It's already 1 hour, so it's a very good Friday session. Okay, so that's all, folks. All right, so Bugs Bunny time. As always, if you have any questions on this, then ask me on Signal. I will start to post some questions on the previous topic, kinetics, and some questions on this in Signal, maybe Google Classroom as well. Even though it's not going to be in your tracking test, or your end of semester test, I should say, then you should still practice those questions anyway, right? Don't only focus on what's going to be in your end of sem exam. Okay, guys, so enjoy your Friday, and I shall see you after the semester break. All right, all the best. Take care.